Log on, tune in, find out. Another good idea from Cambridge.
Okay, thank you for returning for the last session of the day. Our next speaker is Roland Ramsahai from the Stats Lab, who will speak on identifying the effects of treatment on the treated.
Okay, so I'll be talking about the effect of the treatment on the treated and conditions for identifying it from observational data, because it's a parameter that involves intervention, and we can't always intervene to assign treatment. Okay. So to compare, lots of people are familiar with the average causal effect, and the average causal effect is a parameter that can be used to inform policy about treatments on everyone. So if we want to assess the effect of reducing taxes on everyone in the UK, the average causal effect can be used to inform whether that's an effective policy or not. For the effect of treatment on the treated, you use it to assess selective policies. So for example, we want to implement some training scheme to give skills to the unemployed in the UK. You're not going to assess this on the entire UK, because the people that you actually give the training to would vary on socio-economic factors and wealth and other things as well. So, and usually the unemployed are not exchangeable with the entire UK population, so the average causal effect and the effect of treatment on the treated are not usually the same, and you can't use them for each policy to assess the various policies. So usually population of interest, you usually think of the usual intuition in literature is the population of interest is the treated group. So in the literature they normally say ETT, effect of treatment on the treated, is the effect on the treated units. And what I'll show later is that in various studies this intuition is not always correct. In certain studies it's not simply the treated units. So for example, ETT can be considered more appropriately as the effect on the naturally treated. So the effect on the population that would be treated when you don't intervene. So those who would naturally be assigned treatment. So in a randomized study, our treated group is not representative of those who would be normally treated, and ETT is actually not the effect on the treated group. In a cohort study, we don't intervene and assign treatment. So in this case, you can assess ETT can be estimated by the effect on the treated units in a cohort study. In a case control study, you don't directly intervene on treatment, but you do manipulate the distribution of the outcome. And by doing this, you alter the distribution. It's not the same as what would have happened if you hadn't intervened at all. So my proposed definition terms ETT as the effect of treatment on the naturally treated, to be a bit more clear when you're considering various study types. So you know what ETT is. And the natural treated are those who receive treatment when there's no intervention. And now I'll discuss a framework to formally represent what's naturally treated. It's not simply conditioning on t is equal to 1, so we need new notation. So I'll compare the counterfactual framework with the decision theoretic framework to look at the various identifiability criteria in each framework. The counterfactual framework, you have observation that t is equal to t is the usual conditional probability r given t, and you have your potential outcomes notation, which distinguishes observation and intervention by saying RT is some variable which represents the response under intervention, and that's how we distinguish intervention and observation. And they also impose this assumption in the counterfactual framework that R is a deterministic function of treatment and the potential outcome. The decision theoretic framework. So the decision theoretic framework includes additional strategy variables, these sigma, that represent the strategy by which a variable acquires its value. So in this case, if you observe t is equal to t and you don't intervene on treatment, t acquires its value naturally and sigma t is set to this empty set. And this is equal to the usual conditional probability because we don't intervene. For intervention, if you set t is equal to t, we represent this by sigma t equal to common t, and we know that if we set the value of t, then the actual observed value of t is irrelevant because we fix it to that value. So this is, you can simply drop the t from the notation. It's simply the probability of r given sigma t is equal to common t. And these two strategy variables can be used to define the average causal effect. To define the more complicated quantity of ETT, you need this sigma u, which tells you how u acquires its value, and u is an unobserved confounder. And what it does, it's a random intervention. Formally, it's a random intervention that sets u to its distribution in the naturally treated group. And it's natural because there's no intervention on t, and well, I haven't included any other sigma variables for any other variables. So normally that means that we haven't intervened on any other variables. And it's a distribution of u in the treated group, so it's the naturally treated. And u normally represents the characteristics of all of the units, so we know that this is the distribution of the units in the naturally treated group. So we can talk about different study types as long as we compare it to what the naturally treated is supposed to be. So how do we find causal effect? In the counterfactual framework, it's simply a difference in the expectation of the potential outcomes, so the expectation of R1 minus the expectation of R0. And in the decision theoretic framework, you simply use your sigma notation to represent intervention to set t is equal to 1 and intervention to set t is equal to 0. So it's simply the difference in the expectation of these two conditional probabilities. The effect of treatment on the treated in the counterfactual framework, you simply just condition on t is equal to 1, but as I pointed, so it's comparable to the average causal effect, but you condition on t is equal to 1. And as I mentioned before, it's slightly vague because you're not sure if it corresponds to, in various studies, you're not sure if you're talking about the correct parameter. And so, but in the decision theoretic framework, this is one formulation. There are other formulations in the literature, but this is my proposed formulation, that you intervene to set t is equal to 1 and you fix the distribution of the unobserved confounder, which represents the units and the characteristics of the units, to what it would be in the naturally treated group. So you have the difference in the causal effect for the naturally treated group. And to just be a bit more explicit, to compare this to the average causal effect, I include the sigma u, the value of the sigma u in the definition of the average causal effect. So sigma u is empty set, means we didn't intervene on u, so you could easily drop it. But if you include it, you can see a direct comparison that this is the causal effect for the naturally treated, and this is the causal effect for the entire population, because we don't restrict the distribution of u. It comes from its usual marginal distribution. So formally, how do we show why the treated group and these various study types are not the effect of the treatment on the treated? In a randomized trial, you set the treatment. So in the treated group, you set the treatment to be 1, and since this is randomly allocated, u is independent of that, and you have the distribution of u in the treated group is simply the usual marginal probability of u, and this is not equal to the distribution of u given t is equal to 1 in the observational regime, the naturally treated. So this distribution of u is not the distribution of u in the naturally treated group. So in a randomized trial, the naturally treated is not those in the treated group. In a cohort study, you don't intervene on t, so we have sigma t is equal to the empty set, and this reflects the naturally treated because we haven't intervened to set treatment. In a case control study, so the distribution of u in the treated group, the distribution of u given t is equal to 1, is given by this formula here, simply conditional probability of u given t is equal to 1, and r is the response to the outcome times the marginal distribution of r. And assuming this conditional probability remains the same in the case control study and your observational study, you still manipulate the distribution of r. So you manipulate this marginal distribution of r to some p star, And this is not going to be equal to, unless this p star is the same as the natural distribution of the outcome, you're not going to get the characteristics of the naturally treated in the treated group. And if you want to use sigma variable notation to represent strategy, you can just put some you can consider it as an intervention on the outcome in the case control study, and if you didn't intervene on the outcome at all, which is the natural or the observational regime, and you can write this as simply both of them are not the same to show it's not the naturally treated. So that's the various study type. So how about conditions for identifying ETT from an observational study when we have confounding? So this is a diagram that I don't have time to explain formally what the DAG means, but it roughly just has treatment, response, unobserved outcome, and these sigma variables which represent the strategy by which T acquires its value and U acquires its value. In the counterfactual framework, the model usually considers the potential outcomes instead of the unobserved confounders, and the vector of potential outcomes represents the characteristics of various units. So I'll look at various conditions to identify ETT from observational data or cohort study. So one common example is selection on observables, which means U doesn't directly affect T except through X, and this implies that R is independent of the regime given X and T. So the distribution of R given X and T is the same regardless of if you're in a randomized study or cohort study. And the counterfactual framework, you'd write it like this: the potential outcome RT is independent of T given X, and this is one condition that can be used to get an identifiable formula for ETT. This condition identifies ETT and the average causal effect, but you can weaken it to allow this edge by having these conditions, and under this condition you can just identify ETT, but this is all you require to do ETT. Another condition is where X is sufficient for the relationship between U and R, and this is how you would write it in the decision theoretic framework: R independent of the unobserved confounders given X and the, so the response to intervention is independent of U given X, and this implies a similar condition to the previous slide. And just one point to note: normally this condition is called selection on observables because it means that the treatment isn't affected by the potential outcome except through X. But as you can see in this model, treatment can be directly observed. It's just simply that the X is sufficient for the relationship between T and RT. And you can weaken it again if you're just interested in identifying ETT and not the average causal effect, these conditions, and similarly for the instrumental variable model. I guess I won't have time for this. So you can also weaken conditions here. So you can weaken this condition and this condition to identify ETT in the instrumental variable model. I guess that's.
There may be more than one possible choice for your unobserved confounding variable. Would your analysis depend on how that choice is made?
Yeah, so if you extend this model to have multiple unobserved confounders, you may need to consider the intervention to be all the confounders. So here you
Sorry, no, I mean alternative rather than multiple. Different choices you might make.
Well, it's different choices, but all of them would be confounders, right? All of them would I guess this model would be better. All of them would be affecting T and affecting R.
Well, what I'm saying is there can be different structures, different variables, which separately have that structure, but you don't want to put them together in one picture. You want to deal with them separately.
Separately. Well, I guess it should, if each of them is a separate confounder, then you might be able to just consider them separately. And I'm guessing that asymptotically they might come to the same value, but if you're estimating it and you have different data on them.
We'll talk about this.
Are there any other questions? Yes?
I think this is related. I mean, your equations are structural rather than explicit, and in particular, what might be confounders are not identified.
Yeah.
So the question lurking in the background is, would an intervention labeled T change a potential confounder labeled U?
A potential. Well, in this case, the sort of interventions considered on you aren't fixed interventions, so we don't assume that you can be interfered with by fixing it. It's just a random intervention. So you can set T, but as you can see, U is independent of sigma
I
T.
mean, if the confounder is something like gender or date of birth,
Yeah.
then you can't change it. But there may be other factors
Yeah.
which are potentially changeable by the act of
Okay.
being.
Yeah.
So that's the issue that's.
Well, if you incorporate it in the model to see what, like there might be arrows from from those variables, and U might be gender, and there might be other variables. But I guess you'll have to incorporate it and specifically say which conditional independence assumptions hold.